Hello, everyone. Welcome back to Pre-Calc with Ms. Passmore. Today, we are going to continue with section 7.4 and specifically talk about half angle identities. Last time we talked about double angle. Now we're talking about half angle. And yeah, I'm actually kind of trying a little bit of a different setup around. I had you guys watch a couple videos for the last lesson, kind of like a flipped classroom where you get a lot of information flooded at you at first, and then we do more practice problems. So although those videos had problems within them, I didn't tell you exactly how I wanted you to take note. I just asked you to watch them and kind of get a vibe for what half angle identity problems look like. So today we're going to go through a few examples with me. Check me out. Look at how cute that was. I thought it was cute. And so I threw in that little Bitmoji of me and it just flew right in. So today's learning objective will be to develop and use half angle identities. I'm not going to talk about power reduction as that's how the half angle identities are derived in our textbook. I'm just going to get to how to use the half angle identities today and also solving applications using identities as we're working through. So the big idea is that double angle identities are special cases of the half of angle sums, but we're not talking about double angles. We're specifically talking about half angles. So half angle identities result from substituting theta over 2 for theta inside those double angle identities, which we talked about last week. And some of you were struggling a little bit with that, but I think with practice that gets better. But it's literally just a double angle, except we're, instead of just using one angle theta, we're using half of it, hence the name half angle. And then double angle and half angle identities can be used to find exact values of trig values for certain angle measures, which is the whole purpose of this. We want to use something familiar from the unit circle to find things that we don't know. So we're taking unknown angle measures, and we're able to use these identities to come up with an exact value without using a calculator. So again, big idea, use familiar unit circle angles to find trig functions for angles that are half of the measure. Last time with double angle, it was double that angle size. Now this is half of that angle size. So again, use familiar unit circles to find trig functions for angles that are half of the measure. And I'm going to give you a couple examples and you'll kind of be like, oh yeah, that makes sense. Hopefully your little light bulb is going on like mine over there. So you can find sine, cosine, and tangent are three main powerhouse trig functions to find, for example, a 15-degree angle, which is an unknown value on the unit circle, while using the 30-degree angle that we do know, right? And 15 is half of the measure of 30. So do you see where the half angle is coming in? Similarly, you could find a 75-degree angle by using the trig function for 150 degrees, because 75 is exactly half of 150. And although we don't know 75 degrees off the top of our head, because it's not readily available on the unit circle, we do know 150 in quadrant 2. And if we take half of that, we can find 75. Or we could use like sum and difference, things like that too. But this is just another option that we have. Similarly, 22.5, we certainly don't know anything with like a fraction of an angle. We can find that because it's exactly half of a 45-degree angle. So does that start to make sense? We can find these unknown values by using something we do know because they happen to be half of it. So start to recognize when something is half, when something is double. I think that might be a little bit more helpful when you're determining, if you were given a situation where it didn't tell you how to find the exact value, to give yourself a hint of how you would do that. So from the notes from Professor Morvan that I had you guys watch, she derived all of the half angle identities, and she used the value A for it. So I actually just pulled this right from her video. So the half angle identities for tangent, there are 3. Tangent of A over 2 is plus or minus the square root of 1 minus cosine of A over 1 plus cosine of A. Tangent of A over 2 could also be sine of A divided by 1 plus cosine of A. And lastly, tangent of A over 2 could also be 1 minus cosine over A over sine of A. So you have three options for tangent, which usually tangent was looking a little bit more complex, but previously it's only had one formula. For half angles, there are three different derivations. So you kind of have to, depending on the problem, see which is the most simple for you to use, or which one has pieces that you already know or you have readily available that you could use to substitute in. Sine of A over 2 is plus or minus the square root of 1 minus cosine of A over 2. And cosine is plus or minus the square root of 1 plus cosine of A over 2. So all of these are readily available to use for you. You will want to take note of these. You will want to write these down and have these available as you're working through all of the problems, just so that you have like a reference point. And it's very helpful when you're deciding, when you write out what you have and then determining which equation you're going to use. You can kind of, it's like fitting a puzzle together. If you have sine and cosine, you might want to use tangent, this formula, if you have both of those values. If you only have cosine, you might only want to use this. You know what I mean? Just depends on what you have going on. So take this down. Also in our textbook, they use u over 2. It doesn't really matter where u is 2 theta. But they're the same formulas. I do like the way Professor Morvan wrote it out because you can see all of the tangents over here and the sine and cosine over here, whereas this is like cosine, sine, tangent, tangent, tangent. It's a little weird, but they're the exact same things. And lastly, what I want you guys to note, and I know that she talked about this as well, is the plus or minus is dependent upon where this angle lives. So going back to all students take calculus, quadrant 1, all of the trig functions are positive. So if you're in quadrant 1, everything's going to be the positive square root if you're using these. And quadrant 2, t, which is tangent, only tangent is positive, or cotangent is positive in that quadrant. So you would only have tangent being positive over there. Oops, that's S, sine. My apologies. Quadrant 2, all students, A, S. S is sine. I'm sorry. Quadrant 2, sine is positive. Quadrant 3, tangent. Quadrant 4, cosine. So you want to keep that in mind when you're determining whether you take the plus or the minus version. Okay, so like I said, I wanted you guys to take note, and I kept them over here for us as we work through all of these problems. So here's an example using half angle formulas to find exact values. I want us to use a half angle identity to find an exact value for sine of 15. Again, 15 degrees, we don't know off the top of our head. That is an unknown value. However, 15 is half of 30. So we notice that 15 is half of 30, and we're going to want to use that to our advantage. So you always want to think about, sometimes I just like multiply by 2 or divide by 2 and see if that value is a known piece of information from our unit circle. Is kind of like a problem solving process that I go through and think about, is this going to be theta or is this going to be theta over 2? So 15 is half of 30, so that's my half angle. I'm going to use A equals 30. And I'm going back to Professor Morvan where she uses the variable A. I just like it. It looks nicer. So we're going to use, since 15 is half of 30, my half angle, my theta is 30 because 30 over 2 is my half angle. Does that make sense? So, and we're also asked to find sine of 15. So I'm going to substitute in sine of A over 2 is sine of 30 over 2. 1 minus cosine 30 over 2. So A is 30. 30 degrees is in quadrant 1. So I have a positive square root. If I substitute in what cosine of 30 is, which is rad 3 over 2, I have the square root of 1 minus rad 3 over 2 divided by 2, but this is a double-decker fraction. So keep, change, flip it, and you end up with rad 2. The square root of 2 minus radical 3. You can't have double-decker radicals. It's okay. Don't worry. They're allowed to be nested. Divided by 2. And therefore, sine of 15 is this really ugly looking thing. Radical 2 minus the square root of 3 over 2 is what the sine of 15 is. And again, you would have never guessed that. You would have never been able to find that exact value without a calculator. But you can verify this with the calculator. So it showed a little picture of a screen on the bottom right that shows sine of 15 degrees just straight from your calculator. As long as it's in degrees, not radians, is 0.2588190,451. And then if I actually plug in what the square root of 2 minus the square root of 3 divided by 2 is, it gives me that same exact value. So that's us verifying with a calculator, if you felt a little weird about that solution, that it is truly correct. It is true solution. And none of you would have ever guessed that this would have been the answer. Just come on. Gotta be real with me. Okay, so let's try it again, but we're going to use it to find tangent of 15 degrees. Same type of situation. Oops, the answer's right there. Oh well, we'll get there. You'll see the answer seems to be pretty relaxed on this one. But we want to find the exact value for tangent of 15. Again, 15 is half of 30 degrees, so we're going to use that again. So A is still going to equal 30, and just using, looking at my half angle identities, I have to figure out which one I'm going to use. And we're going to say tangent of 30 over 2 is 1 minus cosine over sine. I just kind of picked this one, the very last one, because it seemed to be the easiest one to use. It doesn't, I mean, you're still arrive at the same solution, whichever one you have to use. This one I definitely don't want to mess with because it's got a square root, so it's kind of flip-flopping between the two. But I noticed that this denominator is a little bit more simple, which is why I chose that out of all of them. And then I'm just going to plug it in. 1 minus rad 3 over 2 divided by 1/2 because that is cosine and sine evaluated. Then I have a double-decker fraction, multiply, keep, change, flip. 1 minus rad 3 over 2 times the reciprocal, 2 over 1, gives me 2 minus radical 3. Therefore, tangent of 15 is 2 minus radical 3. Oops, that went a little fast. And like I said, you can use the other formulas too. It's really your choice as to like what is the most applicable to you, of what you're most comfortable with, but you could certainly arrive at the same solution with any of those values for tangent. You could use the second one if you'd want, with sine over 1 plus cosine. Example 6, again, finding exact values using a half angle formula. So we are given a couple stipulations first off in this problem. For cosine of theta equals -7 over 25. So that's my ratio from SOHCAHTOA. Cosine theta is -7 over 25, and theta is in quadrant 3. Find the exact values of sine of theta over 2 and cosine of theta over 2. So now I have to find the half angle for sine of theta over 2 and cosine of theta over 2, given something that's not in a half angle setup. So here, we're going to need to use the information that's given to us. We have to find this and this, given cosine is an exact ratio, and that theta is in quadrant 3. So this is something that I'm kind of a little mad about myself that I didn't talk about as much when we were doing double angle, is setting up an inequality. Since theta is in quadrant 3, we know that quadrant 3 is between pi and 3 pi over 2, if I'm thinking about my unit circle. So I know that theta lives within this interval, right? And then we want to find pi over 2 or theta over 2, so I'm going to divide everything by 2. I could have done the same strategy that I'm about to use right now to determine double angles or just theta from a double angle. So I'd like to set up this inequality based on what I'm given and what I know to find theta over 2. So since it's in quadrant 3, we know it's between pi and 3 pi over 2 radians. And to figure out where pi over, or theta, tripping over my words. Theta over 2 will be, we're going to divide this entire inequality. We're going to divide everything by 2. Oof, that's a really bad 2. By 2. This is a really... We divide everything by 2. We end up getting pi over 2 is less than theta over 2, which is less than double-decker fraction multiplied by reciprocal 3 pi over 4. So theta over 2 is going to be in quadrant 2. This is between 90 and 180 degrees, so it's in quadrant 2. Since it's in quadrant 2, remember we have our little all students, take calculus, or you guys liked all strippers take cash, whatever. Sine is going to be positive, and everything else is negative, so cosine's going to be negative as well. So how I'm going to continue with these is do them simultaneously. So sine of theta over 2 only has one formula. So I'm going to plug in, it's 1 minus cosine of theta divided by 2. I literally just plugged it in. A is equal to theta in this instance. And then cosine also only has one formula, so I'm just plugging in theta, and I'm choosing this to be negative because we know that cosine has to be negative. Now, it was given to us that cosine of theta is negative 7 over 25, which is why I can just plug this right in. So that was a given value. So I have 1 minus negative 7 over 25 divided by 2, all under a square root. This is also equal to the negative value of 1 plus negative 7 over 25 divided by 2, all under a square root, just substituting that guy in straight away. Performing some algebra, I get sine of theta over 2 equals rad 16 divided by 25. And cosine is the square root of 9 divided by 25 with the negative on the outside. That stays the same. And if I continue to reduce that, the square root of 16 divided by the square root of 5, those are two perfect squares. I'm going to have 4/5. And similarly for cosine, those are both perfect squares as well. So square root of 9 is 3, square root of 25 is 5. I still carry that negative once again out here. Therefore, sine of theta over 2 equals 4/5, and cosine of theta over 2 equals negative 3/5. So again, this was an example of where we're given a piece of information. We have to set up an inequality, find out where theta over 2 is going to live, to determine the sign with our radicals. That's really what that's helping us determine. And then plug it in. This information is used to be directly substituted into our equation, and then we just work through with some algebra to get to a final solution. Now I have a couple more. These ones came straight from the textbook, but as I was collaborating with a colleague, I decided to add in a couple more just so you guys can get a really good idea of how the half angle formulas are used. I didn't use everything that my colleague had used, just because we won't be seeing those types of problems. I didn't want to overwhelm y'all, but I think I have two more examples that show you how we can still continue to use half angle formulas to find exact values. So here's a situation which doesn't really tell you, doesn't deal with the inequality like we were last time. But it says if angle A is 135 degrees, find the sine of 67.5 using half angle. So we're given, like A is 135, find 67.5. So you'll notice that 135 divided by 2 is 67.5. So theta, the half angle is 67.5 and the big angle is 135. 135 is in quadrant 2, so we're going to use that information to determine the unknown 67.5. We have no idea how, if you, like without a calculator, we have no idea what the exact value of sine of 67.5 is. So let's start with sine. It wants us to find sine of 67.5. So let's just take the formula right away for sine. So that means we're going to be working with this guy. Okay, sine of 67.5, I'm substituting it in, is sine of 135 over 2 because these are the same thing. So what I'm going to be plugging in for my A is 135. Okay, do you guys see that? Here's A, here's A. Going to be using that. Okay, now we do know cosine of 135. If you don't, look back at your unit circle, pull one up really quick. Look at what cosine of 135 is. It's negative rad 2 over 2 because it's in quadrant 2. So I have 1 minus negative rad 2 over 2 divided by 2 with a large radical over everything. These tend to get a little bit complex, so just stay with me. It's okay. Then I need to get a common denominator. So then we get 2 plus radical 2 over 2 divided by 2, but I have a double-decker fraction, so this one gets, with a little bit of arithmetic, I can simplify this to 2 plus radical 2 over 4 by keep, change, flip, and then simplifying this even further, we have radical 2 plus rad 2 divided by 2 because the square root, remember, square root of 4 is 2. And sign is positive in this instance because quadrant 1, everything is positive, so the final answer for this is also going to be positive. Let's do one more, I think. Maybe I did, I don't remember. So if angle A is also equal to 135, find the cosine. So last time we did sine of 67.5, now we're going to find cosine, right? So we're still going to be using this formula. Starting with cosine. Again, cosine of 67.5 is 135 divided by 2, so my A value is going to be 135. Plugging that in, I have minus rad 2 over 2 for 135 degrees evaluated at cosine. So I have 1 minus rad 2 over 2 divided by 2. If I continue with this, I need to get a common denominator on the top. So I have 2 minus rad 2 over 2 divided by 2 still. This guy still remained the same. Right here and right here. So he's the same, but I have a double-decker fraction. So keep, change, flip it up. I get 2 minus rad 2 divided by 4, all under the square root. And as I simplify that, I get 2 minus rad 2 divided by, this should not be under a radical. This is a typo. It should be like this. Only the radical on the top. My bad. And cosine is going to be positive because 67.5 degrees is in quadrant 1, which means they're all positive. So again, this final value is positive. Okay, and then we're going to find tangent. So if, again, same situation, if we're given A is 135 degrees, find the half angle, evaluated tangent. So find tangent of 67.5 using half angle. So we have to decide which one of these formulas are we going to use. We're still going to start with tangent, so you just have to choose which formula is going to work for tangent. And the last two problems, we got sine and cosine of them. Oh, we actually know them because A is 135. So your choice. I'm going to use the second equation. Like I said, doesn't matter. It just seems a little bit better for me. So tangent of 67.5 is 135 over 2. I have sine of 135 divided by 1 plus cosine of 135. I could really, the one I would avoid using is the first one, and it's kind of up in the air for either of these two. We do know 135. That's a 45-degree angle in quadrant 2, so I have rad 2 over 2 for sine is going to be positive, cosine is going to be negative. So I'm just substituting in sine of 135 is rad 2 over 2, cosine of 135 is negative rad 2 over 2. This is going to give me radical 2 times radical 2 plus 1 over 2 divided by 2 minus rad 2 over 2. If I get common denominators and multiplying, you can't just get a common denominator on the bottom here though, so whatever you do the bottom, you have to do the top, which is why this is so complex. Simplifying this gives me radical 2 divided by 2 minus radical 2, since they both have 2's in the denominators. And then you'd have to rationalize this denominator. So multiply the top and bottom by 2 plus rad 2, which we do right here. Doing so results in 2 times radical 2 plus radical 4 divided by 4 minus radical 4. Since these are conjugates, the middle terms cancel out. And then you're going to simplify the square roots of 4, leaving us with 2 rad 2 plus 2 over 2, because 4 minus 2 is 2. Simplifying this, dividing everything by 2 because they all have something in common, this, and this, leaves with radical 2 plus 1. Now, I know a lot of you are like going to be like, what? I challenge you to take a moment and think about that and see if you can arrive with that same understanding. This is the third. It's also another typo. I chose the second formula for tangent. Again, you could use the third formula. It really is just up to you, since these are, either way, it's going to be a little messy because we have radicals on top of radicals, in term, like double deckers within double deckers. But you should be able to get to radical 2 plus 1. So with these, they're not going to be as complex as the last 3 examples I gave you guys, but I did assign you a little bit less homework than I normally do. 37, 39, 42, 45, 49, 50, and 51 to practice. Again, if you guys have questions, reach out to me. I know a couple of you guys asked me for help. Make sure that you are working on these before it is due on Sunday. Reach out to me a little bit earlier and I'm more than happy to help you, or send me an email and I'll be happy to hold some office hours. Just nobody's been showing up, so I'm not holding my virtual office hours on Google Hangouts. I just wait until somebody has a question. But try them out. They won't be as complex, but you will have some ugly radicals within each other. Okay, and I hope you have a great day. I'll see you next time. Bye.